Okay, hello everyone. So in this video, we're going to be discussing some of the general concepts and some of the general theory surrounding the topic of linear differential equations. And in future videos, we'll discuss ways to solve particular kinds of linear differential equations. Okay, but first some general theory. So firstly, a general linear differential equation is any differential equation of this form here. And it's called linear because the left-hand side of this equation is just a linear combination of y and its derivatives. And for this reason, we call it a linear differential equation. Now, we're interested in being able to solve these kinds of equations subject to these conditions here. And these conditions just specify how should the function y and its derivatives behave at a single point x0. And these are, in other words, called initial values. And so this entire problem, solving this kind of differential equation subject to these conditions, is just an initial value problem. Now, given this kind of linear differential equation and these initial values, we have our first theoretical fact. And that is a very powerful one. Many results in this theory depend on this one, on this fact. And that is that if these functions, these coefficient functions here are continuous and the an of x is not equal to 0, then there exists a unique solution to this initial value problem. So, to any such initial value problem, there exists a unique solution. There exists only one solution. Firstly, there is a solution, and secondly, there's only one solution. Okay, so that's the first theoretical fact. The next is here. It's got to do with another variation on the concept of a linear differential equation. So linear differential equation is called homogeneous if the right-hand side of the equation is just 0, and its order, so it's homogeneous of order n when the leading coefficient function is not identically 0 over the interval that you're considering this differential equation. Okay, then we have the second theoretical fact here, and that is that if I give you n solutions, or in fact any number of solutions to this differential equation, then any linear combination of those solutions is again another solution. So that's exactly what this y over here is. So any linear combination, c1 times y1 plus c2 times y2, cn times yn, will again be a solution to the differential equation star. Okay, so let's just illustrate how this works. So for instance, if I give you this equation, let's say, just a very simple example, if we take y double prime plus y equal to 0. This is certainly a homogeneous linear differential equation of order 2. And I give you two solutions to it over the whole real line. Say y1 equal to sine x and y2 equal to cos x. These are solutions and according to this theorem, which I should just say has a name, it's called the superposition principle. So any superposition of basic solutions is again another solution. So according to the superposition principle, we have the following. So that any linear combination, say y equal to, we can take anything here, we can say 2y1 plus 3y2. So in particular, that's just equal to 2 sine x plus 3 cos x. This again will be a solution to the differential equation. Which in this case is just going to be y double prime plus y equals 0. Okay, so this is the superposition principle. If you're interested to see why it's true, you can just type in superposition principle into Google. So superposition principle for differential equations, and the explanation can be given right there. Okay, so let's move on to the next theoretical concept. So a sequence of functions, y1 up to yn, is called linearly independent over a given interval I if, when I consider this linear combination here, and I find that it's 0, then the constants should have been equal to 0. Let me just say this in a different way. If we consider linear combinations, so C1, Y1 plus C2, Y2, up to Cn, Yn, and we set that equal to 0, we may be interested for which values C1, C2 up to Cn satisfy this equation. And there is always a trivial solution here. Of course, if I take 0 times y1, so I set C1 equal to 0, I set C2 equal to 0, I set Cn equal to 0, or I set all of the C's equal to 0, then of course I'm going to get 0. So at least there's always, there's one family of CIs which make this work. And when that's the only family, when the trivial solution is the only solution, then the sequence of functions here is called linearly independent. So just to repeat that, if I take a linear combination of my functions y1 up to yn, if the only linear combination which gives us 0 is the trivial one, then the sequence of functions is called linearly independent. Okay, so let's look at some examples of this concept in action. So for instance here, we're asked to show that the sequence of functions 1, x plus 1, and x minus 1 squared is linearly independent over the entire real line. So let's see how that works. So if I just let y1 equal 1, and I let y2 equal x plus 1, then I'm dealing with 3 functions here. And I want to show that they're linearly independent. So that means that I have to start always with a linear combination of them. So C1 plus C2 and I want to find out that the only constants which make this valid, which make this 0 here, must be the constant C1, C2, C3, all equal to 0. So just to go back up to the definition here. I have my functions y1 up to yn. To show that they're linearly independent, I have to suppose that I'm given a linear combination which is equal to 0. And then I have to do some logically valid steps to conclude that all of the constants are 0. So that's what's required to be able to show that this property is true. Is I suppose here that I'm given such a linear combination, and then I have to use purely logically valid steps to conclude that all of the constants here are equal to 0. Okay, so on this example, I start here with this linear combination. Now these are specific functions, so I can just I can write out what they are. So it's going to be C1 times y1, which is 1, plus C2 times x plus 1, plus C3 times y3, which is x minus 1 squared. All of that's equal to 0. So here you can just sort this out a bit easier. But what you could, if you wanted to, is you could group the coefficients together and have a polynomial equal to 0. You're welcome to do that. There's also another way, is you can simply substitute in some values. So for instance, if I substitute in x here equal to, for instance, 0, or even 1, or even -1, then I'm going to get rid of the x's and I'm going to have a specific set of equations. So for instance, substituting in x equal to, let's see here, 0, I'm going to get c1 plus 0 plus 1 times c2, which is c2, plus c3, and then 0 minus 1 squared, which is just going to give us c3, and all of that must be equal to 0. So let's just see how this works in one more time. If I look at this equation here, then what is it saying? It's saying that the c1, the c2, and the c3 are such that if I plug in any x whatsoever, I'm going to get 0, no matter what x is. That's what this means here. I plug in any x, I get 0. So in particular, if I plug in x equal to 0, I'm going to get this equation here. And so I must get that the sum of c1, c2, c3 is equal to 0. Right. I could also plug in a different number. Let's plug in, for instance, let's plug in -1. Then I have c1 plus, okay, now c2 times -1 plus 1 is 0. So we can have 0 here. Plus c3 times -1 minus 1 squared, which is going to give us 4 times c3 is equal to 0. Okay, so that gives us another equation. Another thing to do is I plugged in -1, let me plug in 1. If I plug in 1, I'm going to get c1 plus 2c2 plus, and now what I can do is just note that x minus 1 squared when x is equal to 1 is going to give us 0. So here we're just going to have 0. Okay. All right, so in this situation, what we have is a linear system. So these three equations here gives us a linear system, 3 equations, 3 unknowns, and I leave it to you to solve this equation, and you should find that c1 is equal to c2 is equal to c3 is equal to 0. Just using the usual methods of solving such systems of equations. Okay, so let's just go back. We started with such an equation, and then we used some purely logically valid steps to get these 3 equations here, and then we solved these 3 equations using purely logical steps again, and we conclude that the coefficients are 0. In other words, that the only linear combination which gives us 0 is the trivial one. And so what that means is that the set of functions here is linearly independent. Okay, great. Let's do another example. How could we show that sine x cos x is linearly independent over the whole real line? Well, again, we start off with an arbitrary linear combination here. Sine x plus c2 cos x equal to 0. And now I have to do purely logically valid steps and try and conclude somehow that c1 is equal to 0 is equal to c2. Once again, the only linear combination which is 0 is the trivial one. Okay, so let's see how we can do that. Again, we can use the same sort of argument here. If I can choose x to be anything, this equation holds for any real number. So I could substitute in any x here and get an equation which will be valid, right? So let's substitute in, for instance, x equal to 0. Then I have c1 times sine 0 plus c2 cos 0 is equal to 0. And this just gives us that, okay, sine of 0 is 0, so this just gives us that c2 times 1 is 0. In other words, c2 is 0. Okay. We could also substitute in, for instance, pi over 2. And then I would get c1 times sine of pi over 2 plus c2 cos pi over 2 is equal to 0. And again, what we're doing now is we're going to eliminate the cos and just be left with C1 being equal to 0. And so, starting with this assumption, ending with this conclusion, we have shown that the implication that's needed, namely C1 sine x plus C2 cos x equal to 0, implies C1 equal to C2 equal to 0. We've just proved that that's true, so that this is a linearly independent set of functions. All right. Maybe one last example of not dependence, but independence. To show that an implication of statements, if I take A implies B, to show that this is true, in general what we've been doing is we've been starting with A. So I suppose A is true, and then logically conclude that B is true. That's what an implication represents. If A, then B. So to prove such a statement, I have to suppose A, and then conclude B. That's the basic structure of this. But how would I show that it's not valid? To show that an implication is not valid, I have to show that A can be true. There is an example where A can be true and B is not true. So A is true and B is not true. That's the negation, the logical opposite of an implication. So to show that this sequence of functions is not linearly independent, in other words, it's linearly dependent. Maybe I forgot to mention that, but to say that sequence of functions is not linearly independent, it's just to say that it's linearly dependent. We have to try and produce constants, C1 times sine squared x plus C2 cos squared x plus C3 cos 2x, set that equal to 0. And so we have to find, so to prove, to show that the implication is not true, we have to find specific constants here, which are not all 0, and which all add up to 0. How will that help? Because remember, linear independence in this case would mean C1 times y1 plus C2 y2 plus C3 y3 equal to 0 implies all the constants C1, C2 equal to C3 equal to 0. Okay, so that's this red implication at the top here would mean linear independence. So to show that it's not true, we have to find specific C1, C2 such that this is true and not this is true. Which means there are some of the constants here are not equal to 0. So you might remember that cos 2x is equal to cos squared x minus sine squared x. And so that means that we can form a non-trivial linear combination. So since, let's see here, since negative 1 times sine squared x plus 1 times cos squared x minus 1 times cos 2x. So since this equals 0, the sequence of functions is not linearly independent. Which is to say it's linearly dependent. Okay, so that's just to go over the concept of linear independence and linear dependence of a sequence of functions. But what we're interested in is not having, we want one method to determine whether a sequence is dependent or independent, one method to solve them all. And that's why we talk about this concept of Wronskian, of a sequence of functions. So given a sequence of functions y1 up to yn, the Wronskian of y1 up to yn is just defined as this determinant here. Okay, so why do we introduce this concept? Well, here's why. If we had to start off, suppose I was given a linear combination like this. Okay? Then from this, I can produce a system of equations. So I produce this system here where I take the derivative in the second row, and then I continue this process here in the last step, having n minus 1 and n minus 1 here. So all of these will be equal to 0. So given such an equation here, differentiating both sides will give me another equation. So that's how I'm getting the next row here. So from here to here, it's just differentiation once. And then I continue, I differentiate this again. And I continue, and eventually I end up with this equation at the end here, which is c1 times the n minus 1th derivative of y1 added to all the rest up to cn times the n minus 1th derivative of yn. And that must all be 0. So this gives me a system that looks very much like a linear system. So if I write this as a matrix equation, here I'm going to have y1, y2, all the way up to yn. And I'm going to have here y1 prime, y2 prime, yn prime. And I continue this to the n minus 1th derivative of y1 in the first column and y2 in the second column. And in the last column, also the n minus 1th derivative. So I have this matrix times this column vector of constants. And this is all equal to 0. Okay. Now, the thing to see here is that this equation here, this matrix here, it is exactly this matrix. Okay? So we call it W. And this here we can call C, and this here we can call just the 0 vector. Now, what are we interested in showing? We're interested in understanding, is there a condition on W which will give us that C is equal to the 0 vector? Because that's exactly what it would mean to have this implication C1 equal to C2 equal to all the way up to 0, Cn equal to 0. And there is such a condition, and the condition is a very easy one, and that is just that the matrix here is invertible. If W is, so we have this equation, right? We have, just 1 second, let me make some space. We have the matrix equation, which is given by W times C is equal to 0. But if W is invertible, then I can multiply by its inverse to get W inverse times 0 on the right-hand side. And this will just tell me that C is equal to 0. In other words, all of these constants here are equal to 0. So if W is invertible, if this matrix here is invertible, then the only solution to this equation, the only linear combination which adds to the adds to 0 is the trivial linear combination, and that is the condition. And then it's just a nice fact that in linear algebra we can say that a matrix is invertible if and only if its determinant is non-zero. Okay, now just one quick technicality. This is a determinant of functions. So the y1, the y2, the y1 prime, all these derivatives here, they're all functions of x. So this entire determinant is a function of x. So it's not quite a matrix of numbers, right? But we only need it for one value. We only need that the Wronskian the matrix that was written earlier. Let me get it here. This matrix here, we only need that for some specific x. This is a non-invertible. This is an invertible matrix. Okay, because then we can just do this argument. Right. So that just means that what we do here is we ask that this Wronskian is not 0 for just one value. And that gives us this theorem. So given that we have yn up to yn, some functions which are n minus 1 times differentiable over a given interval, if the Wronskian of them is not equal to 0, just for one value in our interval, then the functions are linearly independent. So that gives us a very, very nice method for determining linear independence. Very, very simple method. And let's illustrate this method. Let's show these functions. We showed how earlier these were linearly independent, but it required choosing x to be 0 and x to be pi over 2. But if we had to just consider the Wronskian, we're considering a certain determinant. So we put the first function here, sine x, second function cos x, and then we take the derivative in the first column of the first function, which is cos x, and then in the second we have negative sine x. And so what we get here is that we need to take this derivative, so we're going to get negative sine squared x minus cos squared x, and of course this is just equal to negative 1. So Wronskian is not equal to 0. And so that just means that y1 and y2 are linearly independent. Okay, great. Let's do this on a different example. Let's use it in a more significant way. So suppose we're given these functions 1x squared up to xn. We want to show that these are linearly independent over any interval. Then we can do is we can consider the Wronskian here, 1x squared all the way up to xn. And this is just equal to this determinant here. So we put the functions, so it's going to be 1x squared, and this goes up to x to the n. Now differentiating 1, we get 0. Differentiating x, we get 1. Differentiating 2x, we get 2x. This continues and we get to x, nx to the n minus 1. And then we repeat here, we're going to get 0, 0, and here we'll just get 2, and this continues, and eventually we get to n minus 1 times n times x to the n minus 1. And we continue this all the way down. We get 0. All the way down we get 0 here. All the way down we get 0 here. And eventually the only thing we're going to be left with is the last column, which will get to what? It will, firstly, how many times will we be differentiating? Well, we actually have n plus 1 functions. This is 1, 2, 3, n plus 1 functions. So the number of rows is going to be n plus 1, which means that the last derivative we'll get here is going to be the nth derivative of this. And I hope you'll be able to see that this is just going to be n factorial. And what's the point here? The point is that this is an upper triangular matrix. All of the entries below the main diagonal are all 0. So the nice thing about these kinds of upper triangular matrices is their determinants are extremely easy to calculate. You just multiply all of the elements along the main diagonal, which in this case is 1, 0, 2, just numbers all the way to n factorial. And this is not equal to 0. And because this is not equal to 0, the sequence is 1x squared up to xn is linearly independent. Okay. So this Wronskian is a very interesting and important technique for determining linear independence of functions, which we'll be using a lot in what follows. Okay, thank you.